In this video, we present BOOMER, a tool for blending visual BPH and exact subgraph queries on large networks. We shall demonstrate how to formulate BPH and exact subgraph queries and analyze their results using real-world networks. In the first example, Bob, a biologist, uses a BPH query to find out if C. elegans organism is suitable for studying apoptosis in human. The BPH query vertices in the red box are human genes that are homolog to C. elegans genes related to apoptosis. Bob is interested if these human genes interact in the same way as the corresponding C. elegans genes. First, Bob selects a database called Human PPI, which is a protein-protein interaction network where the nodes are proteins and edges are the interaction between proteins. Then, he loads the index of this network and initializes the query panel by clicking the Add Query button. Next, Bob constructs the BPH query by using the labels in the Human PPI database. He chooses the required labels from the list by browsing, selecting and performing a drag-and-drop action. Edges are then added between the vertices. The BOOMER interface allows Bob to easily configure the minimum and maximum path length of each edge. Here, the minimum and maximum path length of edge, BID, BCL2, is set to 2 and 3, respectively. In BOOMER, edge processing occurs while the query is being formulated. When an edge is processed, its color changes from black to blue and the query processing plan panel is updated with relevant edge information. BOOMER allows query modifications such as node and edge deletion and modification of edge bounds. Here, we illustrate edge bound modification using a left mouse click. The upper edge bound is modified from 4 to 3. Edge information is displayed using a right mouse click. Once Bob completes the BPH query, he clicks the Run button to request for the query results. The number of partial matched vertex sets is shown and Bob can view the results by clicking on the View Results button. BOOMER displays the result in a separate panel where the orange-colored vertices correspond to vertices in the BPH query. The remaining vertices in the results which are colored in blue are the intermediate vertices whose path lengths satisfy the edge bound of the BPH query. The results dialog box shows information of which BPH query vertex is matched to which data graph vertex. BOOMER also displays details of the CAP construction time. In particular, BOOMER identifies all result subgraphs that satisfy the BPH query edge-bound constraints. In this result, vertices APAF1 and BID are connected via the intermediate vertex BCL2L1. Similarly, vertices APAF1 and BCL2 are connected via BCL2L1. Hence, BCL2L1 is an interesting gene that may be used for regulating pathway signaling of APAF1, BID and BCL2. The Previous and Next button in the result visualization panel is used to iterate through all the results for current selected partial matched vertex set. Iterating through the results allow users to view all the possible alternatives paths between each pair of query vertices that satisfy the edge-bound constraints. In the next example, we explore the use of WordNet database for sentence clustering using parts of speech syntax, which can be applied to identify spoken language. WordNet provides 5 parts of speech categorization, namely, noun, verb, adverb, adjective and adjective satellites. Here, we construct a parts of speech graph consisting of adjective, noun and adverb. Observe that the processing of the first edge is delayed as the color of the edges remain black. BOOMER chooses instead to process the next constructed edge NR. This is due to the high estimated edge processing time as there is a large number of match for vertex N. BOOMER implements a defer-to-idle strategy for edge processing. After processing of the third edge AR, the number of matches vertices is vastly reduced and processing of the first edge AN is deemed feasible. Hence, BOOMER processes it. Observe that the query processing plan panel is dynamically updated as query blending occurs. Users can harness the BPH query results to learn lexical concepts. For instance, partial matched vertex sets 72 and 75 yield graphical results with the same topology. The vertices in the two graphs are identical except the match for vertex n. Hence, these two nouns singing voice and low pitch are likely to be related and can be grouped together to describe a concept. In the next example, another scientist Jane is interested to find out if close relationships exist between breast cancer, colorectal cancer and endometrial cancer. An application of this knowledge is in helping to identify common drugs that may be used for these three cancers. Similar to previous example, Jane first loads a database called Human Cancer which contains the PPI network of human genes implicated in cancer. Then Jane proceeds to construct the query using the labels in the Human Cancer database. In this example, BOOMER returns 9 partial matched vertices set. Note that visualization of exact subgraph query results contain the partial one-hop neighborhood of the subgraph query vertices to give additional contextual information of the current result. BOOMER displays a maximum of 5 one-hop neighbors per query vertex to avoid cluttering up the display. Additional one-hop neighbors can be retrieved on demand. These vertices and their edges are colored in gray. Jane can easily browse through the partial matched vertices sets by using either the drop-down selection list or the left and right buttons. We observe that there are multiple gene sets satisfying this particular query. For the current gene set, the gene implicated in breast cancer and colorectal cancer are related to ovarian cancer as well. Hence, drug development focusing on this gene set may not only be beneficial for breast, colorectal and endometrial cancers, but for ovarian cancer as well. In conclusion, BOOMER contains various innovative and user-friendly features for supporting both BPH and exact subgraph queries.